So welcome to the second lecture. So let's look at zeros of holomorphic functions. So we'll first give a lemma that we've really used before, but let's give it more formally and more completely. So have a lemma. So use some open set f. It's a holomorphic function. P is some point in U, and f has an isolated 0 at P. So f of P is 0 and f is not 0 in the neighborhood of P, outside at P, of course. So we know that every 0, unless f would be identical to 0 in let's suppose that U is connected, and if it would be identical to 0 everywhere. So unless it is not identical to 0, unless it is identical to 0, sorry, then you have that all the other zeros are isolated, right? So this is a typical 0 of a holomorphic function. Then there exists a unique integer, unique positive integer, k, and a holomorphic function on all of U, such that g at P is not equal to 0, and oh, I have to change pens, and we have that f of z is basically, I can factor out z minus p to the k. All right. Furthermore, what we get is that k is the smallest integer such that the kth derivative of f at P is not equal to 0. All right. So before we prove that, let's say a couple of things about this. So k. So this is, let's go to the definition. K is the order of the 0 at P, or sometimes we say it's the multiplicity. Right? It's really the correct way of looking at it is that f is of order k at P, and P is the 0 of multiplicity k. But that's just a bit of language. And if the order is 1, it's P is a simple 0. Right? Now, what does order mean? Order means that so if f is of order k, that really means that f of z divided by z minus p to the k is bounded. Right? So is the or it's well it's really the highest k that you can make that makes this bounded. That's really what that is. Of course, if I make k lower, like 0, then it is bounded, right? So it's the highest k that makes this bounded. That's another way of thinking about what the order is. Basically, it's how quickly does f go to 0. There is something hidden in this lemma that might not be immediately obvious from just from the statement, and that's that every isolated 0 of f or of a holomorphic function is of finite order, and the only way to get an infinite order 0, that means that either this would be bounded for all k, or that you could factor out an arbitrarily large power. The only way for that to be infinite is for the function to be just identically 0, right? This is not true for real functions. A real smooth function could have an isolated 0 of infinite order. There's an exercise, I didn't assign it, but it's an interesting interesting note. So if we have, let's say, let me call it something else. Let's see what I called it in the exercise. I called it f. Let me call it something else. Let me call it that we have fg. Let me call it phi. Right? I'll just say it's the real function from R to R. And if we let phi of x be e to the minus, let's do minus 1 over x squared, so I don't have to worry which side I'm coming in. So this is if x is not 0, and I'll just define f0 to be 0. Now this function, you can prove, is actually phi is smooth. It's actually infinitely differentiable, and it has an isolated 0 at 0, right? Of course, it's not holomorphic, right? That's that goes without saying. Otherwise the lemma wouldn't be true, right? So for real function, this is definitely, this lemma cannot be true, at least not as is. So let's look at the proof is easy. I mean, and we've really seen something like this before. We just haven't stated it completely formally before. So proof of the lemma. So if I just look at outside of P, then I can just define G to be f of z over z minus P. This is holomorphic for any k, right? Outside of P, not at P, of course, right? So you really only want to figure out what happens at P. So we need to figure out how to choose that k, so that this G will be holomorphic and non-zero at P, right? So let's expand f at P, right? So on some small disk, right, around P, I have let me write it as Cn as P to the n. Now we know that f has a 0, right, and it has a 0 of certain order. Let's look at that furthermore part of the lemma. That k is the smallest integer, such that the kth derivative is non-zero. These Cn's are given by the derivatives of f at p, right? So we know that up to k, whatever k is, these cn's are 0. So we can really start writing it at at k, right? That's the same thing, because all the previous ones were just 0, right? And now what we can do is, of course, factor out the z minus p to the k, and product of the limit is the limit of the product, right? I can pull out a factor from the limit with no problem. Let me reindex cn plus k z minus p to the n, right? Now this guy, we can let this be g. If this is k, if we let k be that k, the smallest the smallest derivative such that the smallest k such that the kth derivative is non-zero, then we have this thing, right? We define g by this formula we define g by this formula for everything outside of p. We define it by this formula for in the punctured disk, well, actually in the whole disk, even at p, g of p is ck, so it's not 0, right? So we don't have a problem with that. And yeah, that's it, right? Because now we have a holomorphic function. Holomorphicity is local, right? So and it's it's clearly a well-defined thing, right? Even though I defined it sort of in the punctured disk, I defined it both by this formula and by this formula, but they're equal because, well, clearly equal. So now let's check that it's unique. Well, suppose that you had two different k's, right? That you could write it somehow. You could write it, one way, that you could do it this way, and maybe another way, right? So maybe I'll have f of z as z minus p k1 some g1, and it would also be equal to z minus p k2 some g2. Right, and we could assume, without loss of generality, that k1 is less than or equal to k2. Now, if I have this, then what I could do is I could cancel out k1 of these, right, and get that g1 of z is equal to z minus p k2 minus k1 of g2 of z, right? Now that means if k2 is strictly bigger than k1, then I get that g1 at p is 0, right? So meaning it's not one of these g's that I claimed in the lemma, right? Because we said it's g has to be non-zero at p. Okay, so that means that we're done with this. Now, there's actually a stronger thing that we can do, a stronger lemma or a stronger theorem. Oh, let's call it a theorem about if I have a holomorphic function and a 0 of order k. So let's suppose that I have an open set. I have holomorphic function, and suppose that p nu is 0 of f of order k, some positive integer k, right? Then there exists neighborhood v of p, and a holomorphic g defined on v such that well, g is going to be g will be 0 at p. That's it's going to be unavoidable, but g prime at p, so the derivative is not going to be 0. Such that, so what is g supposed to do? G is supposed to be the kth root of f. All right. So in a little bit more fancy language, what this means is that really f, there's g is really going to be a biholomorphic change of variables in some small neighborhood of 0, maybe smaller than v, but in some small neighborhood of 0, there's going to be a biholomorphic change of variables such that f really becomes z to the k, right? So this theorem basically says that locally every holomorphic function is really, if it has a 0, it behaves like z to the k. So if you understand z to the k, you understand holomorphic functions locally, right? It's a really strong statement. All right, so let's prove this, and it's not too difficult actually, strangely. So suppose our v is going to be a disk, around p, such that f z is just not equal to 0 for z in the puncture disk. All right. Now we use the lemma. We can't call it now g, but we're going to call it h. We use the lemma to find h. That is going to be defined on RV, right? So on this disk. So holomorphic such that f of z is equal to z minus p to the k h of z, and also h at p is not 0. Now h cannot be 0 anywhere else on v because f is not 0, and this factor over here is not 0 outside of p, right? So h is never 0 on v. Now if h is never 0 on v, v is a disk. It's simply connected. It's star-like. It's as nice as you want it to be. So that means that we do have logarithms. That means that we do have roots. So we can find. There exists a phi, of course, holomorphic on v, such that phi to the k is h, right? So let g let's define g at z to be z minus p without the k phi, right? Now, clearly, g to the k is f, right? That's clear. That's the way we defined it, and we also can show that the derivative. I mean, at p, g is definitely 0, but so the derivative is non-zero, and this is where we use that phi phi at p is non-zero, right? Because it's, well, it's a root of of h, right? And h was never 0. So if I take a look at g prime, what is g prime? Well, by product rule, right? Prime z plus phi of z, right? And so we see that this factor or this term is 0 because of this factor, right? And this term is not 0, so that at p, right? So g prime at p is not 0, and we're done.